I'd like to thank everyone for joining us in today's webinar introducing the new hydraulic mixing cell feature for HydroGeoSphere, hydraulic mixing cell or HMC. The HMC method tracks the fraction of different water sources in space and time, providing a quantitative measure of those sources at any point downstream. The way that this works is we basically treat every nodal control volume in the HydroGeoSphere model as an idealized mixing cell. So the utility of the HMC approach has been demonstrated in the literature for tracking hyporheic exchange in alluvial channels, calculating groundwater contributions to streamflow, and identifying sources of streamflow. Here we apply the HMC approach to track components of surface water and groundwater during the passage of the June 2013 fluvial flood wave through the town of High River. The HMC results give insights into the transient nature of the passing of the flood wave and the surface water groundwater interactions that may have implications for the design of flood defenses. Before we get going truly here, I'll give a brief introduction to our speaker today, Dr. Mike Callahan. Mike is a senior applications engineer at Aquanty. He has over 25 years of experience in the geoenvironmental sector, including about 20 years of numerical modeling experience, ranging from soil column scale to large river basin scale models. His work has spanned diverse applications such as river sedimentation modeling, salt and pesticide leaching to environmental receptors, hydrologic risk assessment for agriculture, regulatory permitting for mine development, and more recently integrated hydrologic modeling for groundwater supply. Mike, thanks in advance for taking the time to give us this presentation today. Take it away.
Thanks, Braden. Thank you for the introduction. Just one little caveat here. We're not, from my end anyway, I won't be using my camera. We've been having a few issues with Teams this morning, so we'll just sort of leave it off for the presentation, but it shouldn't really affect things that much. Additionally, just in case anybody's sort of on this call that might have been at the conference, I gave this presentation back in November at the joint CWRA-IAH conference on surface water groundwater interactions in Edmonton. And this one, it's I've extended it a little bit with some additional slides, but it's pretty much similar to that. So with that, I'll start my slides. Okay, so I'll need to give a bit of background introduction to sort of some different components of the presentation before I can get into the hydraulic mixing cell application. So I will kind of introduce the case study, which is flooding in the town of High River in Alberta, Canada. I'll give a brief background on HydroGeoSphere for, just potential new users out there that might not be familiar with what it does and how it works. Then I'll get into the model build itself and explain the hydraulic mixing cell method, and then look at some demonstrations of using HMC to explore surface water groundwater interaction during a flood event. Okay, so just to orient everybody, the sort of case study is located in Alberta, Canada. Just southwest of Calgary is the town of High River, and the river basin is the Highwood River Basin. So you'll sort of hear me talking about the Highwood River and the town of High River quite a bit through the presentation, and just so there's no confusion there. In June 2013, all along sort of the Alberta foothills and eastern slopes of the Rocky Mountains, we had quite a large precipitation event. In the northern parts, it was rain on snow. In this sort of area, it was more of just a straight rain event, but I'll sort of introduce a little bit of details from that. And this project was born from kind of a application of looking at risk, hydrologic risk, and it was funded by Agricultural Canada. It had actually multiple aspects to it, all the way from drought through to flood, and this was sort of on the flood application side. So the model itself was built starting in 2015 through 2018, and it was originally built as sort of a standard HydroGeoSphere model. And then later, so maybe about a year ago, we thought it would be a good idea to kind of use it to demonstrate the hydraulic mixing cell capability that we've been using more and more recently at Aquanty. And so just to give a little bit of a sort of perspective of kind of the issue or the risk, is that it's fairly common along the eastern slopes of the Canadian Rocky Mountains that there are urban settlements, both towns and cities, that are built on fairly extensive alluvial aquifers that are highly conductive, typically comprised of coarse sand through to gravel. And they experience a combination of fluvial flooding and groundwater flooding. And it can be quite a complex interaction through the passage of a flood wave. So in 2013, the town of High River saw extensive flooding. I've given the population there just to sort of give a scale of the insurance claims. So it's a fairly small town, about 13,000 people population. And by the end of 2013, 4,500 claims had been made through to the Alberta Provincial Recovery Program. So it was quite extensive in terms of its impact to the town. Just a little bit more background on the town itself, and it sort of feeds into the HMC application later on, is the flood came in from the west. The flood wave was primarily channelized. When it hit the town, it sort of it split into channelized flow heading off to the sort of northeast, and then a large overland wave that exited the town through the southeast. As well, the town is largely dependent on alluvial aquifers for its groundwater supply, which are pulled from the gravel aquifers fairly close to the river channel itself. Okay, so to jump into kind of the background of HydroGeoSphere and just give a little bit of an overview there. So HydroGeoSphere is classified as a fully integrated hydrologic surface-subsurface model. What that means is basically all of the terrestrial components of the water balance are included within the model, from precipitation through infiltration, overland flow, percolation into groundwater flow, and then discharge back through to surface water, which could be streams or lakes or wetlands, and also loss of water through evaporation. And what that kind of looks like, and what we sort of mean by the term fully integrated, is that a response in sort of one component of the water cycle is immediately recognized in another. So you can see the animation on the right, where a precipitation event is infiltrating, the water table is instantly responding to that, as well as the surface water in the center of the model. So that's just a good sort of visual application of what HydroGeoSphere is all about. Okay, so then it's also useful to kind of look at sort of the history, a little bit of the history of hydrologic modeling and sort of where integrated surface-subsurface modeling sits. So if we start on the left, we'd be looking at sort of individual single domain models like surface water models and groundwater models, and being applied separately. The sort of center panel is what we would call loosely coupled models. So those are typically surface water models and groundwater models that have been coupled together, and they pass information back and forth. Good examples of those models would be Mike Shee and GS Flow. And then HydroGeoSphere is sort of at the right-hand side of the spectrum, and that's fully integrated. And what that means is that all of the numerical equations for the solution of surface and subsurface flow are all solved simultaneously together. And to kind of sort of dig a little bit deeper on that concept of coupling. So the term loosely coupled and tightly coupled have been coined in the literature. HGS would be classified as tightly coupled. We tend to use the term at Aquanty fully integrated, but they're synonymous. And what that means is, typically to the application, is that it's a lot more numerically stable than loosely coupled formulations. Loosely coupled formulations can suffer from numerical instability, and I've given just a couple screenshots of references here. So one on the upper right is a benchmarking study that was conducted back in 2017 that included a whole suite of hydrologic models with varying sort of coupling degrees from loosely coupled to tightly coupled, and it really highlighted the benefits of a fully coupled or tightly coupled fully integrated system as compared to loosely coupled. So if anybody's interested, they can sort of take a look at that and see the effects there. And it's important to point out that, in terms of, we're talking about modeling and specifically flood modeling, that HGS has been benchmarked extensively against other integrated models, and internally we've benchmarked HGS against surface water models, and HGS performs very well compared to other surface water flood models, in particular ones that do not include the surface water momentum term. HGS doesn't. It's a diffusive wave formulation. So things like sloshing or changes in elevation around bridge abutments, that sort of thing, aren't solved for in HGS. Okay, so now to sort of look at the case study. So this is the town of High River integrated surface-subsurface hydrologic model. And it is actually, the model I'll be presenting today is the town version. So it's a higher resolution version that sort of spanned the limits of the town itself. We also built a watershed scale model for the Highwood River Basin to produce the inflow to the town of High River model. I will get into that a little bit in the following slide. But so just to give a little bit of background on sort of the magnitude of the event, there was one rain gauge in the catchment, the Burns Creek rain gauge, which was located at that green dot in the eastern slopes of the Rocky Mountains. And over a 2-day period, that gauge saw about 380 millimeters of rainfall. And that then proceeded to flow down through the tributaries into the Highwood River and into the town of High River. And the flood commenced approximately on June 20th, 2013. And so we owe some accolades, I guess, to partners on the project. So we had LiDAR, high-resolution LiDAR was provided by the town of High River, and a fee flow model that we used as our geo model was provided by what was Worley Parsons back in 2013. The geomodel there at the bottom, you can sort of see the zonation of hydraulic conductivity. The town itself sits above the highest hydraulic conductivity zone that sort of ranges from 10 to the minus 3 meters per second. It's primarily sandy gravel. And then there's a sort of larger alluvial aquifer surrounding that that's a little finer, which has a hydraulic conductivity on the order of 10 to the minus 5 meters per second. So very high hydraulic conductivity and resulting in very high surface water-groundwater interaction during passage of the flood wave. All right, so these are some modeled hydrographs compared to what little gauging information exists for the flood event. So there were two primary gauges, one upstream that was on just a small tributary of the Highwood River. It's in the upper left here, and the measured is in blue, and HGS simulated flow is in red. What's important to point out here is that we didn't do any bespoke model calibration for this. It was a demonstration model, and it wasn't really deemed necessary to do calibration. So from there, the next there is no gauge in the town itself. So that's strictly a modeled input there. So we were peaking out at about just shy of 3,000 cubic meters per second inflow into the town of High River, and that would have been just upstream of the town itself. Some additional flood modeling had been done prior to this by AECOM, and we had access to some of their modeled results. So the green plot in the lower left, that's the AECOM 2D modeled flood wave just downstream of the town of High River. And then further down at the watershed outlet, there was a little bit of gauge data in the early stages of the flood before the gauge washed out. And what you'll see here that's kind of interesting and very unique about this flood is that it split as it passed through town. So we had about 3,000 cubic meters per second coming into the town, whereas the channelized flow out was about 1/3 of that, and the rest sort of split and flowed overland to the southeast through a small valley, but really something that just contained a little creek prior to the flood event. Okay, so these are kind of traditional outputs from an HGS model. We're not getting into the HMC results yet, but I just wanted to kind of frame the simulation. So this is the inundation during the flood event. The flood itself spanned about 2 days for the majority of the peak, but flood inundation lasted for many weeks after the passage of the flood. And so you can see the flood comes in from the west, and then sort of splits with a channelized portion going out to the northeast and an overland portion going out to the southeast. The town itself lies basically under the overland flooding portion of the flood wave. So another traditional output from HGS is we can look at effects on groundwater. In this case, it's the water table response to the flood event. As the surface flood wave passes through, there's a direct response in groundwater because of the high hydraulic conductivity of the sands and gravels in the alluvial aquifer. And this is the kind of information that you could use to look at, say, the influence of groundwater flooding on basement flooding, for example. What I'll do here is I'm just going to zoom in on a little spot there. So with this flood event really in 2013, it became quite apparent that basement flooding was a significant component of overall flooding damages. And so especially on the margins of the flood, like if we look sort of on the north margin of the floodplain here, the surface water depths there is surface water ponded in the streets. Those are essentially the lineaments you can see there, but not a lot of surface water extending onto the properties. But if we look at the water table depth, the water table depth is pretty much, is at surface, which would mean basement flooding would would essentially occur in those areas. So this is kind of like a traditional application of HGS, where you could look at both surface water and groundwater flooding simultaneously. But we're here today to primarily talk about hydraulic mixing cell. So I'll use the acronym HMC quite a bit. And what it is it's really an advection-only method of tracking water sources in a HydroGeoSphere model. So, if people are familiar with HydroGeoSphere, it's made up of millions or hundreds of thousands to millions of nodes, computational nodes. It's discretized in space. And what the HMC methodology does is basically track contributions from different water sources at each node in the model. And so those water sources, I'll show examples, but they could be, you could tag precipitation, you could tag overland flow, you could tag ponded water in the model domain, you can tag pre-existing groundwater, and you can basically apply a tracking zone anywhere in the model that you're interested in. So what the HMC does is it tracks those contributions to a node and calculates, the contributions. So that could be, in this example, we might have 60% from one group, 30% from another that is tagged, but then you also have the rest of the water components tagged as well. And then that gets passed on to the next node, so on and so on throughout the model domain. Now, you might ask, how is this different or beneficial to traditional contaminant transport modeling, where you might use the advection dispersion equation? So this is advection only. And one of the advantages of that is that it's not subject to numerical dispersion. So it's very well suited for coarse mesh resolutions where numerical dispersion would be, prohibitively large. So its application is well suited for cases where you've got a coarse mesh resolution, but you want to gain some information on water components. In some ways, it's a little bit analogous to the way particle tracking is often used in HydroGeoSphere or in groundwater models, in that you're tracking where the water flows, where it comes from, but you're not specifically simulating a contaminant. Anyway, so a little bit of history on the use of HMC in HGS. The foundational paper came out in 2011 by Daniel Partington, and it was primarily on explaining the hydraulic mixing cell method, but then also looking at applications of sort of separating different stream flow components. In more recent times, it's had a lot of applications in surface water. So looking at different sources of surface water in space and time, doing base flow separation for hydrographs, looking at hydrograph recession, and sort of a more groundwater focused application was looking at source water protection in Quebec City. So the demonstration I'm presenting here is sort of looking at another potential application, which would be kind of the complex and very dynamic surface water groundwater interactions during flood events. So the two examples I'll show can kind of answer a couple of questions. One of them is, what is the contaminant risk to domestic supply wells from surface water during a flood? That is actually, if a municipality or city is drawing water from its alluvial aquifer, the concern for contamination is quite high during a flood, because the flood wave tends to pick up a lot of contaminants. It can be things like bacteria, so flooding of, say, agricultural lands, and carry that into the vicinity of the aquifer itself. So you could have concerns in terms of quality of water supply immediately after the flood event. So what we're going to do there, take a look at HMC and how you can quantify how much surface water is entering groundwater during the flood and where that's happening. Another concern might be from specifically flooding surface water impoundments. I mean, these could be as simple as stormwater impoundments that do contain quite a few contaminants from road runoff. They could also be more complex, like sewage lagoons or other storage impoundments of potentially contaminated water. And then how HMC could be used to track that impounded water as it gets washed out of a surface water impoundment. So just a little bit of an orientation for essentially for some of the color scales you're going to see on the following animations. So the surface water inflow from the Highwood River is going to be shown in red. So essentially all of these fractions will be shown in terms of a scale from 0 to 1. So 1 being a full fraction and 0 being no fraction. The initial groundwater fraction is going to be shown in blue, and then the initial ponded surface water fraction is going to be shown in green. The rain fraction in terms of this analysis is fairly small, so I haven't really included it here. Okay, so here we are looking at now the surface water and groundwater fractions. So the groundwater is in blue and the surface water fraction is in red. And we're looking at them at two different depths. One is immediately at the ground surface, and so that's the one on the left, and the one on the right is at 1 meter depth. So just for orientation, the water table depth prior to passage of the flood wave was approximately 2 meters. So we're looking at essentially the surface water contribution to groundwater just above the water table. And so you can see that I'll even zoom in on this a little bit in the next slide, but you can see that there is surface water that is penetrating the aquifer to 1 meter depth. And I'll zoom in here on this white area. So if we look at that same animation again, so we've got the ground surface. I mean, it's not unsurprising that near surface, you're seeing surface water fractions of almost 1. And then at the 1 meter depth, it's quite a bit attenuated, but you are seeing some fairly substantial groundwater fractions. Basically, you're getting higher infiltration of surface water in areas that were initially less, had lower soil saturation. So slightly elevated in topography are actually the areas where you get more surface water infiltration. Okay, so let's look at the second example here. So this is going to be the surface water spreading during the flood wave. So the surface water, the initial ponded water in these stormwater ponds is shown in green. The surface water inflow on the left is going to be shown in red, and then groundwater is shown in blue. So we'll get the flood wave coming in as red from the left. It's going to inundate that pond in the middle of the box, and then it spreads the ponded fraction out to the east. And so this would be of a concern if, particularly for something like concentrations of contaminants in soil or onto properties immediately sort of downstream of that surface pond. So with HMC outputs, you get a quantitative fraction of that water from the mixing cell, and then you can also interrogate it in terms of like a hydrograph, how much of that fraction is passing a certain point in time, and how it changes with time. So those are the two examples that I had done up, and I kind of started the presentation looking at sort of what I would call traditional applications of integrated hydrological modeling. So that's where you can look at surface water and groundwater responses, but where HMC sort of really showed its strengths here in this example is that you can then differentiate the water sources with the tracking. So you can separate out, how much is surface water, how much is groundwater, and it can also help sort of delineate the potential for contamination spread. So HMC has found applications in a lot of different fields within hydrology and hydrogeology, from source delineation to base flow separation to contaminant transport. And with that, I'll open it up for questions. I'll just give a few acknowledgements first. So the Municipal District of Foothills, essentially the town of High River, provided data access for the coverage for that model. So high resolution LiDAR was a really key component of the input. And the subsurface geo model was really Parsons. So that was kind of very helpful foundation for building the flood model itself. All right, Braden, I'll pass it back to you.
Thanks, Mike. Maybe we'll just give it a moment and see if any questions appear in the chat here. But maybe to get things started, I could ask a quick question. Given that this model was likely built several years ago and then was rerun with the hydraulic mixing cells, I was wondering if you could just speak to potential runtime increases related to HMC. Is it relatively quick to run, or does it slow things down?
No, I'll sort of, how would I say, caveat that with, so the hydraulic mixing cell did need a smaller maximum time step for the model to solve accurately. So there are metrics output by HMC that essentially allow you to evaluate whether the HMC solution is accurate or not. So it did require a longer time step, which resulted in a longer run time, which I don't think is that surprising. Overall, the original model ran in something sort of like less than a day, on the order of a day, and adding in the hydraulic mixing cell increased that about fourfold. But one thing that I have mentioned to people is that it's by the time you're at this level of simulation, like you've got a fairly advanced model, so it is pretty much a one and done. You set it up, you run it, and those are your results. There's not particularly say a calibration component typically with an application like this.
Okay, thanks. And we do have a question in the chat from Walter, who asks if you can track how much water goes from the snowmelt boundary condition into groundwater using HMC.
Yes. So essentially, it tracks any boundary condition. There's a sort of a series of default boundary conditions that it will track automatically. So those would be your inputs from your model boundary conditions. You can then add in additional tracking. You can also exclude some. I've got some models that have hundreds of boundary conditions, and then it just becomes kind of unwieldy to track everything. So it is, yeah, it's fairly flexible that way.
Yeah, but by default, all boundary conditions are basically tracked as a distinct source of water for the HMC method.
That's right.
Thanks, Walter. Oh, another question from Hyung. He says, great presentation. The main sources of liquid water flux is a combination of snowmelt and rainfall for this flood event. I was wondering how input forcing data, e.g. liquid water flux for HGS, is prepared. What is the temporal and spatial resolution of input data?
It's a good question. So this model, is a little bit old in that I worked on it quite a long time ago. So I do know that we had to do essentially some downscaling of the gauge data to get a little bit more higher resolution precipitation for the watershed model. I do not recall the source for that, but I believe it was there was some climate modeling work that had been done previously. So definitely, depending on your model scale or model size, like its aerial footprint, you do have to tailor the climate inputs to that footprint. So this is, a fairly small watershed, so we needed fairly high resolution climate forcing for that, but I don't recall off the top of my head what that resolution was.
But in general, HydroGeoSphere is flexible to model inputs, right? It's up to the user to define the temporal and spatial resolution of their input data. But you do need to keep in mind, though, that the spatial resolution, or rather the temporal resolution of your forcing data, will also have significant impacts on the model runtime, right? With daily or sub-daily boundary condition forcing data, for example, you would by definition restrict your time step sizes to whatever the temporal resolution of that data is. But in general, HGS can handle whatever you throw at it. I guess I'll also just comment quickly that HydroGeoSphere does have some native winter processes, snow melt, and a snow melt boundary condition, which was mentioned already in the questions. So you can, there is a native snow accumulation and snow melt boundary condition, but typically the liquid water flux data would be prepared offline. The snow melt boundary condition does tend to increase model runtimes as well, so it's generally faster to do a bit of data pre-processing of your liquid water flux data beforehand, and then just apply that directly to the HGS model. Okay, we have another question from Tori. Have you ever done any sort of comparison against using solute transport to estimate flow contributions from defined sources? Leave that one to you, Mike.
Yeah, that's also a good question. It would be a nice comparison, and this model would probably be a good candidate to do that. In general, when we've been applying HMC to client projects, usually the mesh resolution that we're running is just not amenable to advective dispersion modeling. But this model, the lateral mesh resolution is on the order of about 15 meters, which might be fine enough to do some contaminant transport modeling. So yeah, it's a good suggestion.
Another question, actually. Have you done any comparison with particle tracking?
Yes. In terms of the HMC, it's almost like at least the way I would kind of explain it in very lay terms, it's almost a replacement for particle tracking. So instead of doing particle tracking and requiring, so first doing a run with particle tracking, then delineating essentially contributing areas to whatever receptor you might be interested in, the HMC basically kind of supersedes that necessity, right? Because it gives you a full 3D distribution of the contribution of water. So it's definitely essentially easier to set up because you don't have to know where the water is going a priori, and but it gives you similar results, if that sort of explains it. So similar to particle tracking, but kind of a little bit more sophisticated and not requiring decisions to be made about where you want to track things.
Thanks again, Mike. The presentation was really informative. For everyone else here, you can find a recording of the presentation or of the webinar on our blog in the next day or two. If you have any questions about HMC or you're interested in perhaps testing it out for yourself, feel free to reach out to us and we can get you a copy of HGS that unlocks this feature. Okay, have a great day, everyone. Thanks again, Mike.
Thanks.